All right, so this is part 2. We're going to pick up on number 8. So I need to take the beginning triangle JKL, and this time I'm going to translate it, then rotate it. So let's start with our beginning triangle, which was 2, 3, 1, 2, 1, J. K we determined was 1, -1. And L, which is -1, 0. So here's my beginning point. All right, so J, K, L. All right, so that's where I'm starting. Now it says to translate it. So it says to subtract 4 from all of my points. So J prime, K prime,
Autumn Harding, if you're in
L
the
prime.
building, please come to the front office. Autumn
All right, so
Harding,
2
if you're in the
minus
building,
4.
please come to the
So
front
2 minus 4 is -2. 1 minus 4. And -1 minus 4. All right, and then we have to subtract 4 from the y's also. So 3 minus 4, -1 minus 4, 0 minus 4. So there's my next. So now I'm going to plot these in green. So -2, -1, so there's J prime. -3, 1, 2, 3, 1, 2, 3, 4, 5. So there's K prime. And then -5, -4. So 1, 2, 3, 4, 5, -4. So there's L prime. All right. So there is the first transformation, and then we're going to do the last transformation, which is now to rotate 270. Well, to rotate 270, what rule do we follow to rotate 270? So to rotate 270, we have to flip. So it's y. So the y will become my x, and the x will be opposite. So now I've got J double prime, K double prime, L double prime. These notes seem like they take forever because plotting points takes a little bit of time, but in actuality, these probably shouldn't be taking this long. All right, so the y is going to become my x. So this is -1, -5, -4, and then the x value becomes my y, so but I switch the sign. So -2 becomes 2, -3 becomes 3, and -5 becomes 5. So this is my final triangle. So -1, 1, 2. So there's J double prime. -5, 3. 1, 2, 3. And -4, +5. Something ain't seem right. So -5, 1, 2, 3, 4, 5. 1, 2, 3. And then -5, 3, and then -4. 1, 2, 3, 4, 5, which is like out here. All right, so there's my A double prime. I guess it just looks weird because my picture is not accurate. All right, so draw the picture here. All right, so that should be what we have. So we took the original, we split it, and then we rotated it. All right, number 9. All right, so here we go. So a figure in a plane has rotational symmetry when the figure can be mapped onto itself by rotating the figure 180 degrees or less about the center of the figure. So the center of the figure. This is the point. this point is the center of symmetry. Note that the rotation can either be clockwise or counterclockwise. So we're going to determine whether these figures have rotational symmetry if describe any rotations that map. Basically what we're going to do is if you can rotate or turn a figure around the center by fewer than 360 degrees and it still appears unchanged. So if I could take this and I could turn it, how many degrees would I have to turn it before it's exactly the same again? So if I were to take this, first of all, yes, it does have rotational symmetry. Okay, it does have rotational symmetry. And if I rotated it 36 degrees, it would be in the exact same spot again. If I rotated it 72 degrees, it would be in the exact same spot again. If I rotated it 108 degrees, it would be in the exact same spot again. If I rotated it 144 degrees or 180 degrees, it would be in the exact same place. Basically, what I did is I took 360. So this would be if I rotated it this way. So that would be, okay, rotate it there. It's in the exact same spot again. Rotated another 36 degrees, rotated another 36 degrees, rotated another 36 degrees. Okay, so this one does not have rotational symmetry because if I were to rotate around the center, it's not ever going to be the same. In number 11 says to identify the line symmetry and rotational symmetry of an equilateral triangle. Okay, well if I have an equilateral triangle, so if I draw an equilateral triangle, close enough, all right, it's wanting me to have lines of symmetry. All right, well first of all, a line of symmetry is where you can split it where it's identical on both sides. So that would be a line of symmetry. That is not a line of symmetry because it's not going even. That would be a line of symmetry, and that would be a line of symmetry. So it has 3 lines of symmetry. So 3 lines of symmetry. 3 lines of symmetry. I'm just abbreviating. And then it says identify the line of symmetry and the rotational symmetry. Well, 360 divided by 3 is 120. So 360 degrees all to rotate, and I'm rotating 3 sides. So that means that this angle here would be 120 degrees. This would be 120 degrees, and that would be 120 degrees. All right, so identify any congruent figure. Okay, this is way too easy. So identify congruent figures. I'm going to number them to make this more quickly instead of naming every single figure. So I'm just going to call this 1, 2, 3, 4, 5, and 6. So number yours because we can do this a lot faster that way. All right, so what is congruent to 1? So figure 1 is congruent to figure 6. Figure 2 is congruent to figure 3. And figure 4 is congruent to figure 5. All right. Let's see, 1 and 6. 1 and 6 are, let's see, is it a, it is a reflection. So this one is 1 and 6 is a reflection. Why didn't this pick up? Okay, reflection, and it is a reflection over this line. The triangles, the triangle is a 90 degrees rotation, so this is a 90-degree rotation. 4 and 5 is a translation, so this would be x plus 5 and y minus 2 translation. And we can go over this more detail when I see you. All right, describe the congruence transformation that maps this to this. So basically what you're doing is, instead of me giving you the rule, you're going to have to come up with the rule. So what they gave me, it says describe a congruence transformation that maps PQR to STU. All right, so point P is at 4, Q is at 2, -3, and R is at 5, -4. And I'm going to STU. So STU. So point S. So point S is at -4, -5. T is at -2, -2. And this one is at -5, -1. So notice it's not just a simple slide because point P pairs with this one, so it's actually been rotated. So if I rotated it around, and then Q is going to go with T, so this would be P prime, Q prime, this one would be your R prime if you think of it like that. So if I rotated it and then slid it, so let's go, actually these would be double primes, sorry, because this is where we're ending up. So our P prime, if I rotated it, Q prime, if I rotate it, and R prime, if I rotated it. So if I rotated 180 degrees, the rule is that they just switch signs. So -4, 0, -2, 3, -5, 4. So I'm going to rotate it around, and then I'm going to slide it down. So then I'm going to translate it by, if I'll notice, my x values are all the same. The y values, I am subtracting 5. So if I note it like this, oops, sorry, not like that. Note it like this would be the same thing as the vector form this way. All right, number 14, we're almost done. I know this has been a super long set of notes. Determine whether the polygons with the given vertices are congruent. Use transformations to explain your reasoning. So if I plot 2, 2, so 2, 2, 3, 1, and 1, 1. Tiniest triangle ever, ABC. And then let's plot the other one in a different color so it's obvious. So this one is negative, it's 2, -2, 3, -1, 1, -1. So yes, they are congruent. Why are they congruent? Because it is a reflection over the x-axis. So reflection over x-axis. And the last here, what is the angle of rotation? All right, so this is 60 degrees, therefore this over here is 60 degrees. So that means this is 120, which means this is 120. So what is the angle of rotation that maps A to A double prime? So to go from here to here is 120 degrees. All right, guys, I will see y'all in class, and we'll go over anything extra that we need to.